Hello everyone. Today we're going to talk about how we want to sample from the Gaussian distribution, and specifically we're going to talk about a method called Box-Muller method. So this method is related to what we talked about previously in the last video. It is called grid sampling. So we are going to use the idea of the grid sampling in this case to sample from Gaussian distribution. So to start, we also need to have the assumptions. Also, as always, we assume that we can easily sample from a uniform distribution from 0 to 1, because it is very easy to a computer to generate the pseudo number, pseudo random number, and which can get the uniform distribution from 0 to 1. So we will also start from here. And based on this assumption, it is easy to come up with some methods that can help us sample in the Gaussian distribution. For example, we can use central limit theorem. So basically, we can get n samples from the uniform distribution from 0 to 1, and then take the average. This average will follow a Gaussian distribution with mean equal to 1/2 and variance equal to 1 over 12n. But the problem for this approach is that it requires a large number of n, so the computation is very inefficient. For example, if you take n equal to 100, you need to sample 100 data points to get just one single sample in Gaussian. So that's not efficient. And also the second problem for that is that it's not exact. It's just only approximation. So standard limit theorem says that only when n approaches infinity, this average will approach Gaussian. If we pick a relatively smaller n, for example, if we pick n equal to 10, that may not be enough to get a good approximation of the Gaussian distribution. So that's just approximation, not exact. That's the second problem. Okay, and the second approach we can do for getting the sample from the Gaussian distribution is to use the inverse transform sampling, which we discussed in the last video. So the idea is that we sample y from uniform distribution 0 to 1, and then we find x with the Gaussian CDF x equal to y. So this approach is efficient, but the problem is we do not have a closed form solution expression for CDF for Gaussian. So it does not have an analytical expression for sampling. Okay, so now let's talk about this Box-Muller approach. The basic idea for that is, instead of sampling from the 1D standard Gaussian distribution, we can sample coordinates x and y from the 2D standard Gaussian. So why do we sample from 2D Gaussian? Would it be more difficult to do that? We will discuss this later. Okay, so and after we get the coordinates x, y, we can keep x from x, y as the sample, because we know that the in 2D standard Gaussian distribution, its a projection on x direction or y direction are both 1D Gaussian distributions. So the x here will follow a 1D standard Gaussian distribution. So why do we need to discard y here? Because we don't want to have a correlation between x and y. So if we keep both x and y, then we have correlated samples. And because we want to generate independent samples, we only need to keep one of them and discard the other. Okay, so let's give a brief review of what we talked about last time about the grid sampling. So the grid sampling is used to sample any distribution. So the basic idea is that we wanted to divide the region under this curve, under this probability distribution curve, into a bunch of blocks, and each block has the same area. In this case, we divide the area under the curve into 20 blocks, and each one has because each one has the same area, we can say that the probability of sampling each block is are equal in this case. So to do that, because we want to pick any one block out of these 20 blocks, we can sample uniformly from this. We can sample uniformly from this uniform distribution. For example, if we get 0.4, and then we can find which grid correspond to this 0.4. In this case, it's 8 because we have 20 blocks or 20 grids, and multiplied by 0.4, we get 8. So that's the index for the grid we sample. And then we find the x value corresponding to the grid 8, and we get this sample as the sample we want. Okay, so the main idea here is that we want to divide the area on the curve into the equal area regions, and then we want to pick one region and find the x correspond to that region. Okay, so utilize this idea, we can do the same thing for 2D Gaussian distributions. So the first step is to divide the region under this surface into a bunch of equal volume regions. So for example, in this, if we want to divide the regions into 10 regions, and each one with a volume 0.1, we can do the following. We can start from the center, from the origin in XY space. And for example, we use a bunch of cylinders here to denote the boundary of the region. And we want to make because for each region, we want to have exactly the same volume of 0.1. So in this case, we have the volume within this red cylinder is exactly 0.1. And we want to make sure that the volume between this black boundary and red boundary to be 0.1 as well, which means that the volume within this black boundary is 0.2. And we can do the same thing for the region between the black and green. We want to make sure that the region between the black cylinder and the green cylinder is 0.1, which means the volume enclosed by this green boundary is 0.3. And we can get these 10 boundaries because we have 10 regions. So we can index these boundaries of regions by 0.1, 0.2, 0.3, all the way to 1. So these are basically cumulative probabilities starting from the center. So we have like 0.1, 0.2, 0.3, all the way to 1. So we have these kind of 10 boundaries. Basically, it's 10 circles if we see that from the top view. Okay, so now we want to select one region out of these 10 regions. And because each region has the same volume, so it has equal probability of being sampled. So we can sample from a uniform distribution 0 to 1. For example, if select 0.24, then we can find which region it is actually in. So 0.24 is actually in region 3, which is between the black and green, is somewhere here. So we can use the boundary of the region 3 to approximate this selected point, 0.24. So we are going to use 0.3 to approximate this 0.24 and select a uniformly sample a point from the boundary circle 0.3, and so that we can get x and y, and then we keep x, discard y, and the resulting x will be our sample for the corresponding 1D Gaussian distribution. Okay, so here we use the boundary of the region to approximate the any sample point 0.24 in this case, because here we are doing the discrete sampling. We divide the space into 10 regions and sample one region and use its boundary as approximation for that region. But imagine that if we have infinite regions, so that instead of having 10 regions, 10 circles, we have like infinite circles, and that each circle basically tells us what's the volume volume of the region enclosed by this circle, then we can use the same idea to generate samples from uniform distribution, find the boundary, and then sample point from the boundary circle and keep X. That's the general idea. So from this, we can do the generalization from discrete sampling to the continuous sampling. Basically, we instead of dividing the space into 10 regions, we can say dividing the space into infinite number of regions. So the procedure goes like this. So first, we sample a number u from the uniform distribution 0 to 1, and then we find the radius r with the enclosed volume equal to u. So for example, this like in this circle r, we basically say that the volume within this circle is is u. And then we do the same thing. We just sample x and y on the boundary circle r, any pointer here, and keep x. So in these three steps, so first step is very straightforward. We only need to look at the second and third step. So the second, let's first take a look at the second step. To calculate the enclosed volume corresponding to radius r, we basically do the following. So here we write out the 2D Gaussian distribution probability function, and then we need to integral of over the space within the circle in xy space, and because this space has is symmetric with respect to the origin, so we can convert it to the r theta space so that we can get analytical results here. So this is the volume enclosed by this circle, and this volume should equal to u in this case. So we can write r as expression of u, where u follows a uniform distribution from 0 to 1. Okay, so that's the second step. And once we get the second step, once we find the r corresponding to u, it's very easy to do the third step because the third step only involves the uniform distribution on the circle. Basically, we want to sample a angle from 0 to 2 pi. And to do that, we only need to sample a value psi, which from 0 to 1. And then we multiply this by 2 pi. That gives us the angle for between 0 to 2 pi. So to get the x value, we only need to multiply this radius r with this cosine value. So that gives us the x value, which is something we want to sample for the 1D Gaussian distribution. Okay, so so when we talk about this summary, let's go back to our original one of our original problem. Why do we want to sample in 2D Gaussian instead of 1D Gaussian? So the main issue here is that if we want to calculate this integral in 1D for 1D Gaussian, this integral is not tractable. It does not give an analytical expression at the end. But if we have 2D, if we do that in 2D space, then we can convert it in the radial coordinates in r theta space, so that we can get the analytical result for that. So that gives us a nice and clean expressions between r and u. So that's why we want to sample in 2D space instead of 1D space. So as a side note, in a lot of places in machine learning or in mathematics, when we want to solve a problem in low dimensional space, sometimes we want to map to a high dimensional space, and that gives us easier way to solve the problem in the original low dimensional space. So here is an example of that. When we want to solve a problem in 1D space, we convert it to a 2D space problem, and then we solve that, and then take one of the components that give us the result of the for the 1D space problem. Okay, so let's do the summarize here. So basically, this problem is called Box-Muller problem. It takes three approach. So first, we sample a value u in uniform distribution, and then we find R with the enclosed volume equal to this u, and then we sample x and y on boundary circle R and keep x. So here we only need to have two samples from uniform distribution. One is u, the other is psi, and then we can get the resulting sample using this expression. Okay, so that's the basic idea for the Box-Muller methods, and we talk about how we use the idea of grid sampling to arrive at this the method. And let me know if you have any questions, and thank you so much for your attention.